I am Raku, and I'm just about to show you how extra transformers in Bascom from warm audio really sound. Supposedly, they make a difference, but do they really? I've watched a bunch of sound engineers on YouTube saying that these transformers make the sound deeper, warmer, more dynamic, all that good stuff. One guy even mentioned that the effect is so strong that he doesn't always use it. But will you be able to hear the difference? Let's jump into the test now. What we want to do is extract the sound of the transformers from this compressor. To do that, we want to run the original track through the compressor with the transformers turned off, so we can capture the sound of the circuit. Then we will run the same track through the compressor again with the transformers turned on. And then we will solo these two tracks and flip the phase on one of them. This is how we isolate the sound of the transformers. Let's start. First we'll record with transformers off. Broke, you said it would be easier. Okay, now let's turn on the transformers. If you weren't broke, you said it would be easier. Let's switch between the recorded tracks. If you weren't broke, you said would be easier. What we are hearing is the sound of the transformers. Would be easier. If you weren't broke, you said. Okay, let's turn up this track a bit more, just to hear how they sound. Would be easier. If you weren't broke, you said. Would be easier. If you weren't broke, you said. Would be easier. Okay, let's go back to what we had because I want to do one more test. Since transformers react differently based on the signal level they are driven with, our original track peaks around minus 15 dB full scale. So let's compare how the transformers respond to a signals that peak at 0 dBFS and minus 30 dBFS. Okay, let's rename the track minus 15 dB. Duplicate it and set this one to minus 30 dB. Let's duplicate it again and set this one to 0. Now let's normalize this track to the target values, leaving the minus 15 track as it is, since it's already at that level. This one will be minus 30 dB and this one will be 0. Let's move them around so they are in order. 0, 15, 30. We've already set it up, so let's rename this one to minus 15 dB to match the original track. Let's duplicate this group of tracks and then we record these two tracks the same way as before. Now let's render these track groups into single tracks so we can compare them more easily. We can delete the rest since we won't need them anymore. So each original track went to its own transformer tracks 0 to 0, 15 to 15, 30 to 30. Now let's check the level difference between these tracks. First let's take the 0 dB track and its corresponding transformer track. Let's analyze selected items. So here we've got the list. Let's change the order. The difference between them is 41.3 dB. We can easily see the difference on the faders. All we need to do is normalize both tracks to the level of the original track, which is -11 LUFS. The original track will stay at the same level, while the transformer track will be boosted to match the original track level, allowing us to easily see the difference on the faders. So as you can see, we've got 41.3 of the level difference between the original track and the transformer track. Now let's do the same with the other track. So we see that the volume is 34.4, and if we compare it with the previous tracks, we've got 39.8, 41.3. So the stronger the signal we send to the transformers, the quieter the sound becomes when blended with the original signal, so it's more difficult to hear them in the original sound. Keep in mind that we are working at the nominal optimal levels here. The transformers are designed to work at these levels in the most transparent way possible, which is why we are hearing such a big difference in volume in the null test. Now let's compare the sound of these three tracks, just out of curiosity. First, let's remove the last bit of the tracks. Then we need to bring the volume of each track back to 0. And now let's normalize it to -20 LUFS. Let's do the same with the original track. Now we can delete these two tracks since we won't need them anymore. Now we can listen to what we've got. If you weren't broke, you said it would be easier. If you weren't broke, you said it would be easier. Alright, let's add equalizers to each of these tracks so we can have a visual of what we are hearing. Okay, let's start with the original track. And let's listen to it and then compare it to the other tracks one by one. If you weren't broke, you said it would be easier. If you weren't broke, you said. The white one is the original track and the red one is the track generated from the original track. This more or less aligns with what manufacturer claims. There is a bump in the lows and it also adds harmonics in the highs. Let's switch to the 15 dB track. So it's very similar. Let's listen to it. Now let's jump to the 30 dB track. We can see that there is even more lows and less highs. Okay, now let's compare the transformer tracks to each other. If you weren't broke, you said it would be easier. If you weren't broke, you said. There is a slight difference, mostly in the lower end. And now the 30 dB track. A slightly bigger difference in the lower end, and the 30 dB track has a bit less high end. How can we get more saturation out of these transformers? The easiest way is to just hit them with a hotter signal. We can either boost the track we are sending or crank up the send level. The only catch is that if we feed that strong signal back into the interface, we'll be clipping. We would have to get some attenuator to trim the level before it gets to the interface. I'm using my loop throttle monster for that, so we need to dial it in so it doesn't clip. Alright, let's just turn up our track. This compressor has a makeup gain control which boosts the output signal. However, since transformers are the final stage of the circuit, we are actually also increasing the level of the signal going into them. I've cranked the makeup gain to the max, but let's also notice that the compression is turned on. However, since the threshold is set to maximum, we are not actually applying any compression to the signal. You can see it here. So let's turn off the compression now, but the compressor has to be active in order for us to route the signal to the transformers. I'm sure that you can hear it, but let me find a moment with a similar volume. So this makeup gain caused the transformers to saturate more. I used Monster to tame the signal after it leaves this compressor and going into this one, from this one. This reduction in volume happens with practically very little compression. On the meter we can see maybe half of dB of the compression. But to show you that the compression has nothing to do with the distortion, let's turn it on. Not much of a difference. It's just reducing the signal that's going to the makeup gain knob. But of course, the makeup gain isn't used to saturate the transformers. It's there to compensate for the loss of volume caused by the compression. So you won't set it up in a way where the compression is little but the makeup gain is large. What we've done is only for the purpose of this test. One more thing I want to add. Since every analog circuit naturally causes some phase shifts, I wasn't totally sure how much of the sound was coming from the transformers and how much from the circuit itself. You won't really hear phase shift when soloing or in A/B test, but they do show up in a null test, which can mess up with the accuracy of the test. So I contacted Warm Audio support and they confirmed that transformers do not engage an entire separate circuit. The button just enables the transformers to operate within the existing one. That means there should be no extra phase shifts happening. Alright, that's the end of the test. Hope this gave you a better idea of how the transformers sound. Let me know in the comments if you hear the difference when using the button engage transformers. Thank you and see you soon.